to change everything, but it'll just end up being free points. So no worries. But thank you for pointing it out. Okay, we probably passed 2 o'clock now? Yeah, okay, yeah, we're on. So here's my plan, just to let you know. I'm going to try to compress things and quickly finish out the rest of ensembles pretty much today, so that on Friday we can really have some notebook time. Because I feel like I shortchanged you by not having the notebook time with support vector machines the way I wanted to. And then there's like another few bits of notebook to show you for ensembles. Okay? So that's my plan. I'm trying to move quickly. But, you know, at the same time, me moving quickly, I don't want to shortchange your learning during the lecture. So please do ask questions still, especially because I'm trying to go quickly. I might be shortchanging the first explanation. All right, so where we left off was random forests. And the fact that essentially what a random forest is it's a bagging tree. It's a set of trees constructed with a bagging classifier with added randomness. And that added randomness either comes in the form of pick a random subset of features per tree, or for every node in every tree, pick a random subset of features. So that last one has a lot more variability in the formation of the trees. And that last one is the way in which we have this quote-unquote trademark random forest, right? The one that's called random forests. So that's the one by Leo Breiman, who's pretty famous, statistician's kind of famousness. Right. So this is also the one that's implemented in scikit. And here's the thing. How many features do you select? Right? A random subset of features, but how many? So scikit has a default thing, which is that when we select a random subset of features, we do it in proportion to the number of input features to the raw data, right? So if there's m features in the raw data, by default, scikit ends up selecting log base 2m plus 1, so you don't have any zeros, right? You can change that. It's a hyperparameter. It's tunable in scikit-learn. I don't have a strong belief that you need to tune it, but if you know something about the nature of your data, such that subsets of features, like you should have more or less of them for some reason, then maybe you want to try that. Okay. Yeah?
The randomization picking, is that the bootstrapping?
So no, thank you for asking that question. Because there's two kinds of randomization going on. Bagging, just bagging, any kind of bagging classifier, whether it's a random forest or not, that's the bootstrap sampling where every classifier is subsetting the rows of the data. In random forests, either every tree or every node of every tree, either way, is subsetting the columns of the data. So two separate subsettings. The bootstrap sample is rows and it's per classifier. And the other one, the random forest feature subsetting, is columns being subset. And that's every node constructed. Okay. The next part of at least scikit's implementation is that it implements soft voting. If you remember soft voting, it's if your classifier puts out a probability, then instead of just voting everything for your classifier, you can vote probabilities, okay? So this is unique to scikit's implementation. It's not part of the standard random forest, okay? But it's good to understand what's going on. Okay. Random forests are probably the first thing I will try on a tabular data set. Why? Because they're pretty much good enough. Right? You don't want to use decision trees because decision trees overfit. But random forests, by virtue of being ensembles of decision trees, they don't really overfit. They're not terrible overfitters, at least. They're pretty dang fast for most data sets. If your data set doesn't have an insane number of features or a ridiculous level of data points, these are going to do pretty well. And when you look at like any kind of papers with code or a Kaggle situation, the random forest is not going to be the top score. It's not. Will it be 10 or 15% short of the top score? Yep. So if it's 10% short of the top score, it takes 10 minutes to train, even for a huge data set. That's good enough, right? That's good enough to at least see what's going on and see how predictable this data is and know that you've got a reasonable baseline. Okay. So it can handle thousands of input variables because the subsetting is a kind of feature selection, right? So that's good. It has some ways to estimate the importance of features. It is not as nearly interpretable as a single decision tree. Just think of the question that's going on. A single decision tree is just like, oh, here's the set of if statements that represent the tree. It's easy. But in a forest, you have a bunch of those trees. Each one is a different set of if statements, and then there's some potentially nonlinear interaction between those different trees, and that's hard to model, right? So it's not as interpretable, but there are methods to let you interpret what features are important for prediction. We'll talk about those in a second. Okay, we have a way to get built-in validation set or test set, right? That's the out-of-bag estimate because of the bagging part of this. So we can use that out-of-bag estimate, and then we can correct it because we know it's pessimistic. We know out-of-bag is pessimistic, but we can correct it using that 0.632 method or the 0.632 plus method to get an unbiased estimate of generalization error. So tree-based methods are great when you've got missing data. Many kinds of linear style algorithms like a support vector machine, if you've got missing data, you got to deal with it explicitly. If you don't have a measurement, that doesn't make sense in linear algebra, right? You can't just have a blank in a matrix. So you're going to have to do something to handle missing data. That can include leaving out data points that have any missing columns. That can include trying to guess the missing data, which we haven't talked about, but that's called imputation. Imputation is something you can do in scikit-learn. Think about that for your projects. But a decision tree, well, most of the time it's every single node. It's highly unlikely that any particular node is using the missing variable, right? And if you are missing a variable, well, you can just, for a particular data point, ignore that classifier in the forest, right? You can just annul its vote and remove its vote. If you do hit a node that you don't have data on, just don't have that vote. Let the rest of the trees in the forest vote instead. So you're pretty likely to get enough votes to sort out a situation because of the random subset method, as long as your missingness is relatively rare. So it's pretty cool. Also, as usual, we've seen this before, other scikit-learn algorithms, you have a way to deal with rare data, where you can overweight rare class examples so that they make more importance in your error estimates. We're going to see a lot more of that in boosting, a little foreshadowing. Okay, so let me talk very briefly about feature importance. You remember in a given tree, just the score itself is feature importance, right? Things down on the leaf, they're going to generally have lower information gain scores because we pick the single most important one as the root anyway. So by default, the most important variables in a single tree are the root variables. Okay, how do we measure feature importance in our forest? Well, we've got ways to try to weight this over all trees, right? We'll just take the feature importance in tree 1 and take tree 2 and tree 3 and tree 4, and we can combine them in different mathematical ways. So we average over all the trees, and importantly, we weight by the number of examples, right? So this guy has got 75 samples on it. This one's only got 37. So, this one is more important for determining the overall importance across the data set. So we weight by number of samples. We weight and average across trees. I'm not going to ask you to replicate this or ask you questions deriving the thing. I just want you to know there's a method, and it basically involves taking the average importance of a feature across trees. Okay. This, however, is bad when we have mixes of different kinds of variables. In information gain, if you have a binary variable, right, positive or negative class, what's the highest information gain you can have? Anybody remember how this works? Summing that up over all possibilities of class. So if you have a 50-50 situation, a perfectly fair coin, what's the information contained in a single flip of the coin? If you don't remember, it's 1. Right? It's 1 bit of information. What happens if you have a ternary variable? 3 outcome possibilities. Or let's put this in D&D terms. What if you have a 20-sided die? Right? Roll a 20-sided die, there's 20 possibilities. The amount of information contained in the roll of the dice and getting 1 draw from this random process is much higher, okay? A coin tells you about 1 binary choice. That's why it's 1 bit of information. A 20-sided die, how many bits get to 20? It's like, 5, 2 to the 5, 2 to the 6. Somebody with better mental math than me. Is it 2 to the 6? What's 2 to the 6? 64, so that's too big. So maybe it's 2 to the 5. 2 times 2. See? I'm terrible. Here I am wasting time because I'm... Two to the 5th power is 32. Yeah. So it's 32. So it's almost 5 bits of information, right? If you have a 20-sided die, it's almost 5 bits of information to roll the dice to get out the number. Okay? So if you have variables that have many possible outcomes, they're going to have higher information, and that means they have higher information gain. And that means they're going to look more important in determining what the possible outcomes of your whole tree are. Okay? So this method A is only used when we have some kind of evenness across the variables. Like every variable is a continuous number, or all variables are binary categories, or at least binary ternary. But if you have one situation, we've got a variable that's continuous, and then a couple of binary variables, those binary variables are never going to look important. It's always going to be the continuous number. Okay. Another method that is more useful in determining importance, and interestingly, it's a generic method that you can apply to any algorithm out there. It's not just trees and forests. It's called permutation importance. Now, sadly, permutation importance is computationally expensive, because what you're going to do is you're going to try to leave out a variable, do all of your training or cross-validation or whatever it is you're doing, see what your performance metric looks like, then leave out a different variable and do it again. Okay? So if you leave out variables and you see which ones have the best accuracy, then the most important ones are the ones where you see huge drops in accuracy when you leave out one of the variables, right? With trees, or sorry, not for trees, with forests, you have all the different trees you're building, so that's a good opportunity to do permutation importance. But you can use this same method by repeatedly training any classifier. And there are various libraries that will wrap up whatever scikit-learn classifier you want and run permutation importance on it. It could just take a really good long time to do it for obvious reasons. Okay. So here's like an example of feature importance. So this is the data set. Can you see this at all? Yeah, I can almost see it. So this is a data set that tries to predict economic measures, right? It tries to predict whether or not predict whether or not somebody has been college educated or something like that from a bunch of economic indicators for that person. I forget the exact thing. You can go click on the link and find out, okay? But when you do the method A, feature importance, what you see is that there's this really strong thing where things like income, which is, of course, a continuous number, look like the most important things, right? And if you add in a continuous random variable into the mix, where there's a fake dummy variable that you can see here maybe says continuous random, it looks really important, right? It's a pretty important variable since these are sorted feature importances. So obviously a random variable that you just stuck in there has no prediction power, right? You stuck in the random variable. It's just random, it's just dice. It has no relationship to the thing you're trying to predict. So to see its feature importance way up the list like that is bad news. So this is method A, where we use weighted sums of the feature importances of every tree, right? And you see this issue. Okay, if you use permutation importance, where we repeatedly leave out a variable and we measure importance by the decrement in performance when we leave it out, you'll see that those random variables have low feature importance. Okay? They're not fooled by the fact that a random number, a random continuous number, by virtue of having lots of possible outcomes because it's a continuous number, which therefore means it's a high information thing to start with, that's why it fools method A. Okay. That was maybe a little too long on this topic, but know that you can find feature importances both in classifiers in general through permutation importance and specifically in the random forest world. All right. Does anybody have any questions before I go to boosting classifiers? Yeah.
The second one is so much better than the first one, at least when it comes to throwing variables. Why isn't it a catch-all, and why does this happen?
What if it takes you 3 hours to train your cross-validation? And now you want to do permutation importance and multiply that 3 hours by however many different features are in the data set, and you got to leave one out every time you redo it? That's why. Computation time. So if all of your features are similar, like all features are continuous numbers, F it, use method A, right? It's when you have a mix of continuous numbers and binary variables as inputs that you get into trouble. But good question. Anything else? Okay, we've been talking about bagging as a way to build a classifier. There are other ways to build classifiers. And just like we're bagging, we can put whatever kind of classifier we want in a bagging setup. And then there's particular kinds of bagging setups that have names like random forests. Boosting is the same way. Boosting is a different way to build an ensemble. Okay? So just to kind of put it in context, at this point, when we get to boosting, we're actually approaching the current trends in machine learning, all right? So way back when, the bleeding edge, high research stuff was original neural networks. And, over time, this has evolved so that you get this picture that looks like, okay, at least boosting was like full-on research stuff almost until like 2018 or 2019. Boosting is also the kind of thing that's won an awful lot of Kaggle competitions, okay? So it is, even if it's not the bleeding edge, even if the bleeding edge has been taken over by neural networky kind of stuff nowadays, it's still a powerful enough algorithm that it wins contests. So what is boosting? Boosting is like bagging in that we've got a bunch of classifiers. But the key intuition that makes boosting different than bagging is that every time we make a classifier, we're making it to fix the mistakes of the last classifier in the ensemble. Okay? So in bagging, all the classifiers in the ensemble, they're all independent. We're forcing them to make independent mistakes by giving them different resamplings of the data. Now, instead of resampling the data, what we're going to do is we're going to correct the learning of each classifier so that if we're training classifier 6, we look at the mistakes classifier 5 made, and we make classifier 6 do better at those particular instances that were mistakes. Okay? That's the key intuition of boosting. Again, we're doing the same thing as bagging, we take a weak learner. A weak learner can be something that's just a little bit better than chance. That same sigmoid curve applies, right? And then we boost together the ensemble. We train it so that each successive classifier is going to do better than the last one at the mistakes the last one made. Okay, so there's two kinds of boosting, the adaptive method and the gradient method. As you might guess, the gradient method involves gradient descent. So again, what is a weak learner? Typically, we put in things that are computationally cheap that can probably do better than chance. Okay? So a decision tree, sure, but with boosting in particular, because boosting is so effective, we can even go down to the level of a decision stump. Just one node. K nearest neighbors, okay. Naive Bayes is probably more common if we're not using stumps. Naive Bayes is pretty simple. We haven't really talked about it, but I can do it in 16 seconds. Okay, if you have positive class points and negative class points, Naive Bayes simply asks, what is the mean of those points? When given a test point, you ask, which one's closer? Whichever mean is closer to your current location, that's your class. Naive Bayes, the end. Okay, so really simple methods. So the original ADA boost or adaptive boosting technique is from back in '97, but it's gradient boosting that's the cutting edge, right? It's gradient boosting, especially as implemented in highly computationally efficient versions that started to win Kaggle prizes. Just to be clear, gradient boosting is really good at tabular data, okay? So if you have a data frame, a pandas data frame of data, gradient boosting is a good choice as a default attempt at stuff. It's less good at images and sound files and stuff like that, okay? It's the tabular data that it shines on. Okay, let's look at the idea. We have our training set coming in, and we train our first classifier. Then what we're going to do is we're going to look at the mistakes this classifier makes. So if there's data point 12 and data point 67 that we screw up, we're going to make those data points worth more. We're going to weight having an error on data point 12 and data point 67 as, say, 3 errors for each one of those instead of just 1 error. Okay? And we're going to use that weighted training sample to train classifier 2. So then classifier 2 does perfect on data points 12 and 67, but now it messes up data point 18. Okay? When we build the next one, we're going to weight data point 18 as much more important to solve, and so on and so forth. Okay, we are iteratively setting these weightings, right? And the output at the end is going to be a weighted sum of the beliefs of every one of these classifiers. So we're going to take these ones, and we're going to run them through. Whatever they give me a test data point, run it through all the classifiers in the ensemble. And I'm going to weight each classifier according to its misclassification error in the case of AdaBoost, right? AdaBoost just says, how much do I believe this guy? Well, this guy had like, a 12% error rate, misclassification error. This one had an 18% misclassification error. This one down here maybe had a 9% misclassification error rate. I believe them proportional to their error rates. That's what AdaBoost is about, right? How many errors did I make in the data set? Okay, gradient boosting, it doesn't use the misclassification error because misclassification error, well, remember the shape? No gradient. Okay? So that's where gradient boosting has got something which is a linear algorithm. Okay, so just to make your life confusing, the boosting thing has two separate weighting systems. That's what I just drew out. Weighting system number one is shown in green. As we are constructing each member of the ensemble, we're reweighting the training data's importance, right? We're keeping the stuff that was a mistake from the last time around, we're making it much more important for us to learn this time. That's the sample weight in green. After we have constructed the ensemble, our error rate on the training set sets the classifier weighting. And the classifier weighting is used at prediction time. Run the test set through the classifiers, get their outputs on each test data point, and use a soft voting, right, or a weighted majority vote, a soft voting system, where we believe classifiers proportional to their misclassification error rate on the training set. Conceptually, are we there? No, I can see lots of eyebrows. Let's work a sample, right? Let's see if working some math helps. Okay, this is the algorithm for AdaBoost. So we're going to start by training a learner with a starting data set. We're going to create this weak learner, and we're going to find out how bad is it on the training set. That's its error rate. Okay? So it's error rate on the training set. We're going to store this value here, which is essentially just a natural log of your error rate. Okay? We're going to store it in a variable alpha for later, because that's going to be useful. Now we're going to reweight every data point in the data set. Okay? So the next step, that's T+1 means building the next classifier. In building the next classifier, we're going to make the importance of this data point go up with an exponential if we misclassified it, or decay with an exponential if we got it right. So what that means is if we have, whoops, I need to type right here. So if this is building classifier 1, and this is building classifier 2, and this is building classifier 3, and this is whatever, data point 1, data point 2, and we look at their importance, the data points start off flat, and if we do good, then we start to decay. And if we mess that up, then we're going to go up. Okay? And then we'll start to decay again with these exponential things, right? So we've misclassified right here on data point 1, and we send it up. okay? And likewise, data point 2 is going to do its thing. It starts off here, and maybe, we misclassify it immediately, and then it starts to decay again, right? Okay? When it's test time, this is our situation. We kept all those alphas around too, the misclassification rates. And we're going to use those alphas again to weight the output of our whole ensemble as a sum over all the individual members of the ensemble weighted by their misclassification errors. Ready for some run the numbers? Okay. So again, there's two weighting systems here. Green for sample weighting, yellow for classifier prediction time weighting. All right, so let's do it. Here's a toy example. We've got some data set. Ready? So a data set looks like this. We got positive class and negative class instances. We're training decision stumps, right? Decision stumps have one and only one node. So we're going to do the decision stump thing. We're going to check the two variables. There's two variables here, x1 and x2, right? So we're going to sweep all the possible values of x2. We're going to sweep all the possible values of x1. We're going to look for the one possibility that's got the lowest misclassification error. Let's say it's that one. Okay? So that's what the decision is going to be. Now, what mistakes did we make? Well, we made 3 mistakes, right? Here's 3 positive class data points that are on the negative class side. Right? We're going to reweight the data. Okay? We're going to calculate our error rate. It's 3 out of 9 data points. That works out to making this alpha equal to 0.42. Okay? So we're going to take those mistake data points, and we're going to bump them up by e to the 0.42 power. Okay? So now, those 3 mistake data points, they're worth more. They're worth e to the 0.42 more than these other data points. And these other data points, they have actually gone down. They're not just 1 importance where there used to be. They're e to the minus 0.42, smaller than 1. They've decayed slightly from 1 in their importance. So you can see that by the fact that they're smaller than they were over here. Okay? Build your classifier again. Now, as we're building the classifier, we take into account the importance of each sample in calculating a misclassification error rate. Okay? So again, we sweep x2, we sweep x1, calculating that error rate using the weighting. Okay, maybe that's our decision boundary now. So what errors have we made? Well, these guys are on the wrong side. Okay, so we now have, and these errors, right, they're weighted errors. So this is, even though this is 3 data points that are wrong, it's not worth 3/9, it's worth less than that, because these are e to the minus 0.42 down from 1. Okay, so you calculate again, you get the new alpha, and now these data points are worth more. These data points have all decayed in their worth from the last version. Are we starting to get the idea? Okay. So last time, we do it again. Let's say this is the version that now pops up. Okay, we've got a single error here, and then 2 errors here. So still 3 errors, right? But again, these things have been decaying. So for instance, these have decayed twice now, right? They decayed from here to here, and then they decayed from here to here. So our error is lower, and everything reweights again. Yeah?
Is there a point with this algorithm where eventually you just kind of start going in circles?
Yes, you can absolutely, depending upon the data set and the classifiers, start going back on yourself and essentially reweight, paying attention to some data points you made mistakes on, forgetting them for a long time, and then coming back to those being the important data points. Absolutely can happen. There's no natural stopping point here. How many classifiers are you putting into your boosting system? Up to you, hyperparameter. Okay. So again, at test time, once you've done all this training and you're ready to run a test set, the output is a weighted sum with those alpha terms of each classifier's classifications. Okay. So when we're all said and done, we take those 3 classifiers, we put them together, we get something that looks like a decision tree. It's piecewise linear because it's composed of a bunch of decision stumps, right? So that's pretty cool, right? The output is those alpha terms that we came up with multiplied by each one of those classifiers' outputs. So it's relatively efficient, right? A decision stump's not the most efficient thing by itself, but you're only doing it for one of them. If you have a lot of features to test, it can slow down, but it works pretty well for reasonable numbers of features. Okay, so that is eta boost. Eta boost is based on the misclassification error, right? Setting those alphas is based on misclassification error. Misclassification error is not gradient descentable. So to set alphas using gradient boosting, we use a linear loss function instead of the misclassification error. And XGBoost, won a bunch of Kaggle, right? The other thing about XGBoost is we can use it for regressions because that linear sum, it doesn't require misclassification error to build the alphas, right? So it's a linear alpha. And so we can put together cart decision trees and make a forest of cart decision trees to do ensemble regression. It's kind of fun. You can also, by the way, do random forest regression. So 2 ways to make regressions with ensembles. Okay. Because it's got gradient descent, we can add in a penalty term. So as well as the linear combination of the outputs, we can add in a term penalizing the alphas from being too big, right? Just like we would penalize weights to try to reduce complexity. Okay. So Importantly, the whole reason that gradient boosting exists, besides the fact that it enables you to do gradient descent and regressions and all that kind of stuff, is that, remember I told you decision stumps, they're okay for small numbers of variables, but when you have 10,000 variables, it sucks rocks because it's exhaustive search in a 10,000 vector space, right? So it's not just gradient boosting, but a bunch of software algorithmic infrastructure to approximate gradient boosting that enables you to deal with internet-sized data sets. You got 40,000 variables? No problem, feed it to LightGBM. LightGBM implements a low memory usage, high speed system for doing those stumps, so we can deal with that high number of variables. Now, scikit recently picked this up and implements the same idea in what's called the hist gradient boosting machines, hist gradient boosting classifier, hist gradient boosting regressor. Here's the key intuition of how LightGBM and the scikit version work. Instead of having continuous variables, we bin the variables. We turn them into histograms. So we just chunk it up so that you've got, 256 levels that are possible in this continuous variable between 1 and 10,000. And you just turn every continuous number into its binned value, right? We discretize the continuous. That's the magic. By discretizing the continuous, we have fewer exhaustive search things to do. It's not hard. It's just the programming to make that happen at scale efficiently. All right. So we kind of did it. We got all the way through ensembles today. Woohoo! Just remind yourself what ensembles are in general. We've talked about bagging and boosting as two ways to build them. But for both of these methods, the important thing is that each classifier has to make different kinds of mistakes. That is, they have to be diverse or statistically independent, or however you want to couch that criteria. They also have to be accurate in the sense that they're better than guessing randomly. They don't have to be much better, just a little better than guessing randomly. Right. When you have that situation, you can pile together a gazillion of these bad classifiers and make one good one, or bad regressors and make one good one. So in general, what we've talked about for ways to make diverse classifiers is subsetting training examples, the rows of the data. That's called bagging. Subsetting the input features. That's the random forest algorithm. And a version of that that we just talked about, which is reweighting. Actually, no, sorry, it's not a features thing. It's an examples thing. Reweighting training samples. That's what boosting does. You could also do it, and we haven't talked about this at all, by having stochasticity just in your individual classifiers. This is kind of the neural network way, right? Neural networks have weights. Their weights, as we will discover next week, they have to start somewhere. They start at random values. Usually. Sometimes random values that have particular PDFs, sometimes just uniform random, whatever. And that randomness means every single chunk of a neural network is a little different than any other chunk of the neural network. And no two neural networks are alike even when they start out. And that means that The learning setup drives them to different parts of the solution space. Okay? So we'll see that next week. All right. So yeah, these guys are good. They're pretty good and generally very usable. So definitely a first stop. Anybody have any questions that I can answer? Yeah? Yeah, every single element of the ensemble is overfitting, but the ensemble as a whole is not, right? Because every single one is making mistakes separately.
But in the processing, aren't like training the first one and then train the second one?
Yeah.
But you're keeping the information from the first one.
Absolutely. In the end of the day, your boosting ensemble has all of those classifiers, the first one and the last one and everyone in between. And like we were talking about over there earlier, you know, it can be the case that ensemble, like classifier 67, is making the same kinds of mistakes that classifier number 3 was. It can be cyclical, right, in that sense. But in the end, we weight all of those classifiers' predictions to make an output for the entire ensemble.
But aren't you, like the second one is going to be better than the first one and the third one's going to be
The second one's going to be better than the first one on the ones the first one made mistakes on. It could start to make mistakes in different data points that classifier 1 didn't mess up because of that reweighting. You got it.